We're going to begin the second stage of glycolysis. Remember, now we have 2 molecules of glyceraldehyde 3-phosphate. And we are going to, in our minds, say that every step that we're doing from step 6 on, 6 to 10, is going to happen in duplicate. So we have 2 molecules of glyceraldehyde 3-phosphate. Glyceraldehyde is a highly oxidized molecule. Look, it has an aldehyde, an alcohol, and a phosphate on it. So what we're going to do is we are going to take an inorganic phosphate. An inorganic phosphate. And what that means is just phosphate in solution. Remember, the buffer in your cell is a phosphate buffer. So remember I said that protons come in and out, phosphates come in and out. We're not necessarily going to account for where they're coming or where they're going because that's our surroundings. So here we are, we're going to add on another phosphate. And what happens here is this is actually going to be an oxidation of carbon number 1. So by putting this phosphate on to carbon number 1, we are oxidizing it. And when you are oxidizing, you have to have something that's reduced. And that's going to be an NAD. It's going to get reduced to NADH. And so this is a middle money molecule. We're going to exchange it. Remember I said it's like a foreign currency where we're going to take it to our electron transport chain. And remember, this is in the cytosol still. But we're going to transport it into the mitochondrial matrix and have it go through the electron transport chain. And we're going to be able to get, for every NADH, we're going to be able to get 2.5 ATPs. So that's the exchange rate. So we will see that we get some, out of an oxidation, we get some money, even though we have to change it in. So that is step number 6. But let's take a closer look at it. This really happens in 2 steps. First, we have the oxidation. And NAD is going to be the oxidizing agent. And look at the energetics. This is a delta G. All right, and I want to explain something here. This not means 1 molar concentrations. That's standard conditions. So if you have a delta G naught, that means everything's at 1 molar. This little prime here means everything's at 1 molar but our pH, and that would be pH 7. So do you think in the cell this is happening at 1 molar concentrations except for the hydrogen ion? No, 1 molar is huge. So these numbers that I'm going to be giving to you, these delta G naught primes, they're sort of artificial, but they're very helpful in guiding our understanding. So what does this negative 43 kilojoules per mole mean to you?
Spontaneous.
It means it's spontaneous. And actually, just relatively, it's pretty spontaneous. That's a very large negative delta G. So this is what happens first. And then here, we're going to phosphorylate that acid. And so we get this acid anhydride. Those of you that have taken organic chemistry will recognize carbonyl, oxygen, and another sort of, this is sort of like a carbonyl. That's called an anhydride, right? Not so stable. Not so stable. Anhydrides are not long-lived in aqueous environments. But look at this delta G naught. That's positive 49. Well, what if you add them together? Negative 43 and positive 49. You get positive, right? So this should be, if you couple these 2, it should be non-spontaneous. But remember, these are artificial numbers. I actually took the time to find out at cellular conditions, at the concentrations that we have, what is that delta G overall. And so under cellular conditions, the delta G is negative 1.29. So it is spontaneous slightly. when you have a value of delta G so close to 0, what's driving the reaction forward is going to be Le Chatelier's principle. So we use our book values to kind of give us a guide, but we have to use it with a grain of salt. So overall, this has a positive 6.2 kilojoules for 1 mole of glucose. That would be double that, 12.4 kilojoules per mole of glucose. But again, under cellular conditions, it's negative 1.29. So basically, it's close to 0. So Le Chatelier's principle, and that's why we have these reversible signs here. Let's take a little closer look at what's happening at the site of the enzyme. Now, where did we see, or what amino acid residue would this be with the sulfur and the hydrogen on it? Oh, it's written right here, cysteine, right? Why do I put that in there? Cysteine is going to be acting as a what? What is it doing there? It's acting as a nucleophile. What other amino acid residue acted as a nucleophile before? Serine with the oxygen, right? So sulfur is just like oxygen, has a lone pair there, and that is going to attack the carbonyl of our substrate. And then what happens is we form a substrate enzyme complex. There's actually a covalent bond. And then here is our nicotinamide ring of our NAD. And what happens is this is going to break down, and this hydrogen hydride, so the electrons are going to go into this nicotinamide ring and stabilize that. And then we're going to end up with the sulfur and carbonyl bond. And so the phosphate will actually come in and attack that and break that bond. So then we have this very unstable intermediate, and the sulfur breaks off. So I'm not going to ask you to memorize this, but I do want you to notice a couple things. The sulfur of cysteine can act as a nucleophile, just like the serine did. Another thing I want you to notice about this mechanism is that the nicotinamide ring is picking up a hydride, hydrogen with the electrons. Bless you. And because that's pulling the hydride off, then we get this, this group here with the carbonyl and the sulfur, which makes it much easier for the phosphate to attack that carbonyl, because the sulfur is pulling electron density away from this carbon, making it much more easy for it to be attacked by the oxygen on a phosphate. And again, we make an unstable intermediate. So again, the sulfur is acting as a nucleophile. The nicotinamide ring is picking up a hydride. And this is sort of a mixed anhydride here. It's not very stable. So let's go to our document camera and summarize this. Again, I have a double arrow because that delta G is so close to 0. We're going to call it an oxidation. You can add phosphorylation on there. But that inorganic phosphate is that PI, that PO4H, or HPO4. That's that inorganic phosphate, PI. And then the NAD comes in and NADH comes out. Basically, what I want you to know is that it happens in 2 steps. It's the oxidation is the spontaneous part, the phosphorylation is the non-spontaneous part. And when you couple them, in reality, it comes to close to 0.
Could you say that again?
Sure. The take-home message for this reaction is that it's a 2-step process. You have an oxidation and a phosphorylation. The oxidation is spontaneous, gives off a lot of free energy, and the phosphorylation is non-spontaneous. When you couple them, it's pretty close to zero. So remember, this is happening in duplicate. So what have we gotten out so far? 2 NADHs. Can I go back to the PC? So in the next one, and I apologize for this typo from the text, that what we have is our first gain of energy. We call this a substrate level phosphorylation because we are giving the one of the phosphates, the phosphate that we just added on, that very unstable anhydride. Remember, this is called an anhydride right here. Right, this part is called an anhydride. And what we're doing is we're breaking that apart and giving the phosphate over to an ADP to make our money molecule, ATP. Remember, this is happening in duplicate, so our investment is paid back. Remember the lady from the beginning of the chapter when I showed that video? She said we're paying back that investment. All right, so we're going to call this is a new vocabulary word, substrate level phosphorylation. And what that means to us is that we are transferring the phosphate from a molecule with what we call a high phosphate group transfer potential to a molecule with a lower phosphate group transfer potential. A substrate level phosphorylation is when we are transferring a phosphate from a molecule with a high phosphate group transfer potential to a molecule with a lower phosphate group transfer potential. Phosphate group transfer potential is a measure of the energy of hydrolysis of that phosphate group from the molecule. I'll say that again. Phosphate group transfer potential is just a measure of the energy of hydrolysis of that phosphate group from your molecule. So if we look at the amount of energy that we're going to get by taking the phosphate off of our 1,3-bisphosphoglycerate, this molecule, it's negative, by chopping off this phosphate, it's negative 49.3 kilojoules per mole. If we look at ATP, to take off one of the phosphates, it's negative 30.5 kilojoules per mole. So ATP has a lower phosphate group transfer potential, 49.5 or 49.3 to 30.5. So by taking off the phosphate from 1,3-bisphosphoglycerate, you get out 49.3. By putting it on the ADP to ATP, you have to put in 30.5 kilojoules per mole. Again, I'm not going to ask these numbers. I just want a qualitative view. You don't need to remember these numbers. I just want you to know, oh, I get more energy out of taking the phosphate off of this guy than putting it on to this guy. I want to mention something else. This enzyme, which I won't require you to memorize, is phosphoglycerate kinase. Did you hear the word kinase before in any of the other important enzymes? Hexokinase. And what reaction did that catalyze? Putting the phosphate onto glucose, right? Hexokinase was for the first reaction. and it took ATP, took the phosphate alpha ATP, and put it onto our glucose, carbon number 6. So what do you think a kinase does? If this one, what does what?
Phosphorylation.
Yeah, what it does is it transfers a phosphate through ATP. And then we get our 3-phosphoglycerate down here. Now the difference between that and our entry molecule to step 2 is down here we have an acid. All right, now the next 2 steps are going to be getting ready steps. But before we do that, I'll let you work on your sheet. I want you to notice something about the naming. I named 3-phosphoglycerate, glycerate 3-phosphate. It goes back and forth. It doesn't matter. So now we're even Steven in our energy. Although we got out 2 NADHs so far, so we're a little bit ahead. But we invested 2 ATPs in stage 1, and now, because this is happening in duplicate, we get back 2 ATPs. So it's almost like when you guys study for this, fill out 2 stage 2s. So have your stage 1 up on top, and then print out 2 stage 2s, and have them like parallel, so you get to in your mind that that's happening twice. You guys good?
Simultaneously, or does like
Well, when you break, you have a. How do I say this? So you're going to have 2 glyceraldehyde 3-phosphates that are going to come from stage 1. Remember, in stage 1, we get these 2. And then they're both going to be brought up. Yeah, simultaneously.
at the same time? Okay.
Yeah. I mean, there's lots of molecules that this is going on. Okay. Let's go back to the PC. So I mentioned the next 2 steps are going to be getting ready. And what we mean is we're going to, by these 2 steps, we are going to create a very strained molecule, a molecule that has a very, very high phosphate group transfer potential. Our phosphoenolpyruvate has a very high phosphate group transfer potential. So in the combination of this isomerization and the dehydration that's happening next, we are creating our PEP, which is really, really a very strained molecule. So the first step is what we're going to do is take this phosphate and put it in the middle of the molecule. Mutase is the name, the ending usually for something that's going to isomerize. So this step is an isomerization. So we go from 3-phosphoglycerate to 2-phosphoglycerate. A little bit angrier. And then what we're doing in step 9 is a dehydration. You're taking hydrogen from carbon number 2 and the OH from carbon number 3, and we're making a double bond. And this is a super angry molecule, PEP. You have a double bond, an acid. Look at this. I mean, this is just a lot going on in this one little molecule. All right, I don't have a lot to say about these, but other than PEP is a high energy molecule. So what I'm going to do is let you copy down yeah, we're going to take a hydrogen from here and this OH, these 2, to make this double bond. Remember, these are reversible reactions, so the streamer is running flat. But in the next step, there's a huge waterfall. Yeah, water, we don't account for that. The water molecule that's being lost, we're in an aqueous environment, So I didn't even bother to do like an arrow out of water. I mean, you can put that in there, but I really, actually they do show it in the slide, plus water. But the next reaction is the coolest one. You guys ready for that? PEP, a very, very angry molecule. Why do I say that it's angry? Because when it gets rid of this phosphate, it is going to give off negative 61.9 kilojoules. That is a huge waterfall. To take and cleave this phosphate off, to go from PEP just to pyruvate. Never mind we haven't gotten to putting that phosphate onto ADP. We're giving off 61.9 kilojoules. That means that PEP has a huge, huge phosphate group transfer potential, because this negative 61.9 is the energy released when you remove the phosphate. So phosphate groups are transferred from molecules with a high phosphate group transfer potential to molecules with lower phosphate group transfer potentials. So we give off negative 61.9 kilojoules to take off this phosphate. We take up only 30.5 kilojoules per mole from ADP to ATP. Single arrow. Why do you think there's a single arrow here? Look at the difference. How much energy are we giving off? Lots. 30.5 kilojoules, or 30 something. I can't do that math in my head. A lot. All right? It's a lot of energy. And so when a lot of energy is given off, then we are going to control it. So this molecule, this reaction is controlled, and this is our last reaction, and it is our pyruvate kinase is the enzyme, the last enzyme that I want you to memorize for this pathway. We're going to talk about it a little bit more. This reaction is irreversible, and we'll talk about what molecules control it in a moment. Before we go to our handout, I want you to recognize this is our pyruvate. This is what's going to go to the mitochondria. This is where we're going to do a pre-citric acid cycle reaction to get it ready to go into our citric acid cycle, into our Krebs cycle. So we are done. We are now netting 2 ATPs because this is happening in duplicate again. This is, again, another example of coupling reactions, very spontaneous to non-spontaneous. But here, unlike the other ones, the energy is so much from that coupling that it is going to be a very negative delta G. So again, what happened in stage 2? We made 2 molecules of pyruvate, and that molecule is still a holder of energy because we're going to further process it and get more ATP from it. So 2 pyruvate from each molecule of glucose. We have a net of 2 ATPs because we put in 2 ATPs in stage 1, and how many did we get out in stage 2? 4, because each time we got 2, right? So 4. There's 3 points of control: hexokinase, PFK, and pyruvate kinase. We're going to take a look at that closer.